I used an array of items to hold the benefit and weights for the knapsack right here. And I used an array of bit set to act as my string of genes that are either on or off, which is right here. The first thing I do is I generate a set of items to take. That's right here where I do all that. And then I generate an initial population. That generate R bits is just generating random population, a set of zeros and ones. Once I have an initial population, I start to do crossover and mutation and evaluations. The first crossover is between the current gene I and just some random gene. Sorry, it's this one first. And this is based on whether or not we have a maximum index yet. And if we have a maximum index, then the population, this should say equals, that's fine. Then the population gets crossed over with the maximum, like the best one. But then we find the best parent. Well, I mutate it inside as I do the crossover. After I do the crossover, I mutate, and it doesn't always return a mutated gene. Sometimes it'll just return the same one. So my mutate is right here. So it's a roughly about half 50% of the time. It's not exact, but I wanted to do that just because of the small sample size. I just wanted to see mutations occurring. So then the next thing that we do after we do our crossovers, mutations, evaluations, we evaluate to see which one is going to become the best one. Basically, it just finds the best one out of these with the highest score and a weight that's less than the maximum weight that we can carry. And then we just loop through this. I chose 200 times. Just arbitrary number, large number. It seems to work out. And then I just print out the final result, the resulting best genetic sequence that represents the best solution to the knapsack problem. And that's it. So this is what it looks like when it's running. Let me take out that so it doesn't jump out. And we can throw those out there, it's fine. Well, that's fine. Okay. So this is what it looks like when it runs. So the best solution is this genetic sequence with a benefit of 321 and a weight of 241. And you can see this is the set of knapsack items right here. So if there's 30 of these items and it said 0000000000001, it would say, oh, well, then that means it's got a benefit of 4 and a weight of 24. If I turned this one on, it would add these two. And the evaluation function is right here, and it just takes your bit set and an array of objects, and if the bit is on, it totals your benefit and it totals your weight. If the bit's off, it just doesn't do anything at all. It just loops through the whole thing, and then it returns a pair of your total benefit, total weight. For the crossover, all I do is take the first half, or not first half, a random crossover point based on the size of the input, and swap it with the first half of the first one, and then swap the second half of it by decreasing from my size to my crossover point. So it just does the simple single point crossover. Mutation showed you that. Generate R bits. It just generates the zeros or ones randomly, and that's that for that. Yeah, super fun. But yeah, that's the entire knapsack problem, and it works relatively decently. I like it. 249, 342, and it's not gonna always give me the same exact answer, but it's going to give me a pretty good answer, usually. So if I can get it to run, there it goes. So yeah, thank you for listening to my presentation.